Hydroelectricity. The task was to find out which design produced more energy. We built two models, as seen on the screen, which both produce electricity using copper coils and magnets. It works because, as water is pulled onto the wheel, it, as well as the magnetic field, spins inside the coil, making the electrons in the coil speed up. In turn, it produces an electrical charge. We then decided to conduct tests to see how well each model worked, and to compare them against each other. Our control variables were the same amount of water, pressure and time, the same multimeter, the same magnets, the same copper wires, the same plastic paddles, the same type of wood, the same bearings, the same metal rod, the same level of waterproofing, the same weather conditions, as much as we could control them. Our independent variables were the different models, length of time water was in contact with the wheel, and amount of water. The independent model variables were the number of magnets, the amount of copper coil, the placement of the magnets and copper coil, the number of paddles, the weight, and the number of bearings. Our dependent variable was the multimeter. The materials used for the models were wood, acrylic plastic, magnets, copper coils, metal rod, glue gun glue, wood glue, a waterproofing spray, vegetable oil, ceramic bearings, and screws. The tools that we used to make them were a hacksaw, a handsaw, a rotary tool, a bandsaw, a drill, a glue gun, and a jigsaw. The equipment we used to conduct our experiments were a multimeter, measuring jugs, a funnel, a hose, a timer, and water. To find out which one of our models worked the best, we needed to conduct an experiment. The hypothesis. We hypothesized that Model 1 would produce more voltage, watts, amps, and resistance, as there are more magnets, so more voltage, watts and amps, and therefore a stronger magnetic field. It should have more resistance because the copper wire is longer than on Model 2. The experiment. Firstly, we placed Model number 1 on the ground and connected the multimeter. Then, we turned the hose on. As we pointed it at the paddles, we started the timer and took the hose away when the timer reached the set amount of time, 2 seconds, 5 seconds, 10 seconds. We recorded how many volts, amps, watts and ohms were displayed on the multimeter. We repeated that process for each time increment, 2 seconds, 5 seconds, 10 seconds. Next, we measured out the set amounts of water, 250 milliliters, 500 milliliters, 1 liter. While the multimeter was connected, we poured it onto the paddles through the funnel. Then, we recorded how many volts, amps, watts and ohms were displayed on the multimeter. Again, we repeated this process for each amount of water, 250 milliliters, 500 milliliters, 1 liter. We dried model number 1 off and put model number 2 in its place. We carried out all of the tests we put model number 1 through, but on this model. Finally, after finishing the tests, we dried model number 2 off. These were the results. As you can see, model number 1 outperformed model number 2 in most of the tests. Prior to conducting the experiments, we hypothesized that model number 1 would produce more voltage, amps, watts and resistance than model number 2. And by carrying out the test, we proved our hypothesis correct on the majority of the tests. Using this knowledge, we can gather that more magnets and more resistance produce more electrical charge. In conclusion, model number 1 is more effective than model number 2.
Real-world applications. As model number 1 is more effective, it could be placed and secured at the foot of rain gutter drains, and the electricity could be stored and used at a later date when needed, such as when a power cut occurs. If the model was built by a machine like a 3D printer, it would produce more electricity than when it was built by hand. This could be used in rainy countries such as England, as it would be useless in dry areas with next to no rain. If built on a large scale with lighter materials, it could also be used as a wind turbine.